Hi, everyone. So we both submitted talks about data flow analysis in MLIR. So we're all rolling this into one. Jeff's going to start off talking about the framework and how he designed it and the formal justification behind it. And then I'll give an in-depth example of how I used data flow analysis to implement a pass in Flang.
Sweet. Thanks, Tom. Yeah, I'm Jeff. I'm from Modular, as you can see on my shirt. And let's just dive right in. So quick agenda, because this is a bit of a longer talk, given that we merged ours together. But it worked quite well because there's a lot of overlap. We're going to talk about why we need a new framework in MLIR. We're going to talk about some of the design of like an extensible, composable data flow analysis framework. Like what exactly does this mean? What does this mean for the framework? And what does this mean for the API? We'll look at like some of the internal code around the components of the framework. I'll do a quick example of SCCP, which is a common compiler optimization, sparse conditional constant propagation, and how it was implemented with this framework in upstream MLIR. We'll then pass it back to Tom, who is going to do a quick background on Flang and talk about an in-depth example of how Flang is using the framework to implement some cool analysis. So some background, why do we need a new framework? Specifically, why do we need a new one in MLIR? MLIR has had a motley of tools to perform data flow analysis. There was this like forward sparse analysis, not really framework, kind of like a structure that previously existed that was used to implement SCCP. There's like a few things hanging around about like dead code elimination and like live analysis that were just kind of scattered around MLIR, but no like unified framework for doing data flow analysis across different kinds of domains like LLVM has with the attributor. So, and the other reason why MLIR doesn't tend to require the kind of whole program, whole function analysis that LLVM or other compiler infrastructures does is that with a high-level IR, MLIR really encourages building like operations that concisely contain the concepts and semantics that you're trying to optimize in like a local set of operations. So you tend to just have the information available in the ops to perform these optimizations. Now, raising is a separate issue. But it turns out that, yeah, we do kind of want to write like, lifetime analysis on pointers. We want to write like memory effects analysis on lower level programs. We're not always going to get the nice high level like lin-out loops that we get from an ML model. And especially if you're building a programming language tends to be quite unstructured and quite low level compared to the IR that comes out of a model. And if we look at building and adding more analyses to MLIR, it's like, okay, we got analysis here, here, and here, and they don't talk to each other. They don't live in the same framework. They don't speak the same language. So we want to add a new framework to MLIR that allows you to write all the analysis using the same framework, compose them together to find results that each analysis would not have been able to do on their own. Also, it's like there's a phase ordering issue here too. And we want to start building an analysis, a library of analyses in MLIR and compose these with things that exist out of tree because, I don't want to have to put my dialect in tree just to be able to compose analyses together. That's antithetical to the extensibility MLIR is supposed to provide. And that hopefully it is generally applicable to all data flow problems. So quick background on like classical data flow analysis. It comes in 2-ish, 4, 8 forms, depending on how many like dimensions you add to your box. There's sparse data flow analysis. This data flow analysis is where you have a state. This can be like the constant value of an SSA value or the integer range of an SSA value. And transfer functions are computed across operations. You take the integer ranges of all the inputs of an operation. Oh, it's an add, like do the range arithmetic, and then you set the integer range of the result. And so it's sparse because it's going across SSA USTF chains. You have dense data flow analysis, where you have a dense state that contains a bunch of information about the state of the program at a particular point in the program, and then you compute a transfer function across that operation. So if you have like memory, right, and your dense state can contain the current values of all the stack allocations in your function, that's in your dense state. Your transfer function across a store would be take the value that's being stored, put it in the state, and that is the state after the operation. So there's some like math here if you want to read it. Then there's handling control flow, and typically we write data flow analysis on, for example, a basic block. And what you do is when control flow is crossing from one basic block to another, you join the states based on the SSA values or the dense state from all incoming points. So in sparse analysis, for each in MLR, we have block arguments, which are like the same as find nodes semantically, but they're a little nicer to work with, in my opinion. You take the sparse states of the operands of the branch operation in the predecessors, and you join all of them together, and that forms the sparse state of the block argument in the successor, BB1 here. In the dense state, you just take the dense state at the end of each basic block and join them. There's also this concept of like a top-bottom state. A top state is basically if you join this state with any other state, it becomes that other state. I might have like flipped these symbols. I'm not a mathematician, but yeah, I might have flipped these symbols. But anyways, there's these states where the join of this state and any other state is going to be that state, or it's like overdefined, where you can't extract any more information from the program. And this is in a pessimistic analysis. So in a pessimistic analysis, you start assuming you know nothing, and then you sort of add more information and then at the end of the analysis, you take the information you have, and then maybe you can do something with it. In optimistic analysis, you start assuming you know everything, and you slowly reduce the size of the state. So then we have the concept of a fixed point. So data flow analysis, when you have cycles in your control flow graph, is implemented using fixed point analysis, where we provide an initial value for the states, and we just start calling these transfer functions. And each time you have an update, you have to go and find what's dependent on the state, keep calling it, and then eventually you hit a fixed point where the state update stops or the state stops updating. And that's when all the states reach a fixed point, the analysis concludes. So what do we mean when we say extensibility? Well, there's like 3 letters in this equation, S, P, and F, right? The state, like what are the state variables? What are the program points that you can attach state variables to, SSA values, points in the program before and after each operation, and the transfer function that is on every operation. We want each of these 3 points to be extensible in some way. So, and then what does composability mean? Composability means that I can take 2 analyses that both work on 2 different state variables. For example, liveness and constant value, or constant value and range analysis, and combine these together into the same analysis. So one transfer function can refer to states can refer to different state variables, and they're not just constrained to one state variable. What does composability mean for transfer functions? Well, there's this math here that says we meet 2 functions together. Concretely, what that means is, let's say you have constant propagation at MLIR, which is called the op folder, right? And so if your op doesn't implement the fold hook, it just goes, oops, I don't know what this is, overdefined, and then it doesn't get a constant value. But if you have an outer tree dialect that actually has more interesting folding semantics, and you as the dialect author know how this op should fold to its result, or how constant propagation occurs across this operation, but it doesn't quite fit into the paradigm of the fold hook. You still want to be able to tell constant propagation, hey, actually, for this op, I do know what to do, but you don't want to go and fiddle with the upstream implementation, and you have to justify, why do I need to add this extra callback into this function? Oh, because I have an outer tree use, and the reaction you'll tend to get is like, well, I mean, no, I don't think we need this, right? And so we really need a system where people who are living outer tree can compose with stuff that exists in tree, instead of resorting to, well, they're not going to accept my change because they don't believe the use case. I just have to copy all the code and change it. That's not something that we want to encourage. So what does that actually translate to, this composing or meeting a transfer function? So we start with this equation from the dense data flow analysis. You sub in FOP. And this is where the math gets a bit hand-wavy from my perspective. But I've talked to someone who knows abstract interpretation, and he tells me this is correct. So you have an issue with it, ask me, and I'll point you to him. Kind of just like distribute the meet operator. And then what you get is you have the result of the new state computed with one transfer function is meted with a state computed with another transfer function. So for example, if one transfer function concludes the state is overdefined, I don't know what it is, but another one concludes it's 4. When you meet these together, the meet of overdefined and 4 is 4. It's like set intersect in this case. Oh, that works. Sweet. And what does it mean for data flow to be generalized? It means that a transfer function can access the entire program state at any given point, right? I can start from the bottom of a function and read the constant value of I don't know, like a callee somewhere, right? Or I can start at the bottom of a loop and read the memory state at the beginning of the loop. I can do anything I want, and so you can, in theory, can implement any equation you want. The issue here is that we can't re-invoke every single transfer function in the program on every single program point when anything in the state updates. So we have to implement a kind of dynamic dependency graph that is determined as you run the C++ code. And these functions are arbitrary C++ code, so there's no like guarantee of convergence or anything. You're on your own. If it doesn't converge, that's on you. So from this, we can sort of derive the required framework API. We have to be able to define new program points that have state variables attached to them. We have to be able to define new kinds of state variables, and they have to implement the join and meet binary operators. There's some like math that says that these have to be monotonic, and if you implement a comparator, then maybe you can check this too. And then implement like, give me the top state, give me the bottom state, and these can be used to provide initial values for states in the analysis. We have to be able to define and inject new transfer functions that have access to any state variables, and then the solver has to like construct and manipulate a dynamic dependency graph. As a bonus, it should be hopefully not a nightmare to debug, because debugging data flow analysis not really giving you the right result or the result that you think that it should be getting is kind of hard when all you really have is like a dump button or like a print everything button. Now, for those of you who saw the What's New in MLIR presentation, there's this new debug actions framework that lets you like put a breakpoint inside my data flow analysis. That would be really cool to integrate when I figure out how that works. So let's dive into the internals of the framework. There's 4 components, 3 of which represent the extension points. There's a generic program point, which is a storage uniquer user, and for people familiar with like the MLIR ins and outs, a storage uniquer is how attributes are implemented, how types are implemented, and locations. They provide like hashing and uniquing, and you just get a pointer to something. So with a generic program point is a storage uniquer user. He's like, oh, I have like a controlful edge. Now you have a unique identifier to this controlful edge in the entire program. We also require that all program points have a location so that we can debug it. Analysis state is like the abstract class for all state variables in the program. And it also contains a list of dependent transfer functions and update callbacks. So when this state gets changed, please do all this stuff. And then this is how the transfer functions can tell individual state variables how to like invoke them when they get updated. There's this data flow analysis class, which implements 2 methods, visit and solve, or visit and initialize. Visit is like the transfer function, and initialize is, because we have a dynamic dependency graph, the initial state of the dependency graph is nothing, so nothing will run. And so each analysis gets called on its initialize hook to like set up the analysis, and so that when it gets invoked the first time, it starts to build and propagate through the program. And then there's the data flow solver, which just implements the fixed point iteration and all the memory management required by the framework. So program points are MLIR operations, values, and blocks. And these are provided out of the box because they're super common. Oh, regions too. But what else could you actually conceptually have as a program point? And specifically, you're asking, what do I want to attach a state variable to? Well, maybe it's a controlful graph edge. Instead of saying this block is live or this block is live, you want to say the edge between these 2 blocks is live. Because if you have a conditional branch or you have a block with multiple predecessors or successors, maybe only one of those branches are live. So you want to attach a state to it. This is how you do it. Analysis states have to implement this API here. You have join, meet. I think meet hasn't been upstreamed yet, so some of this stuff is still, there's one patch that's still in flight. And there's some other like little functions here that you can see. There's an on-update callback, which is optional. The solver does some of the analysis dependency management for you, but if you want to be more efficient, there's this callback here. So an example of an analysis state is this predecessor state, which in dead code analysis represents the live predecessors of a region. So region control flow in MLIR doesn't have the kind of encoding that CFGs do in MLIR. Region control flow is really defined by an interface. And predecessor state also happens to be useful for call graphs, right? What are the live calls of a function is encoded in this analysis state subclass. So it implements the meet and join, which are pretty much just set, union, and intersect. But we do also want to have an undefined state in this case, because this is optimistic analysis, where we say we don't actually know all of the predecessors. For example, if a if you're talking about like a public function, which could be called from anywhere else, like a library you link it to, we don't know all the predecessors. So we have an extra flag here because you can't really represent the set of everything with a small pointer set. And then we have child analyses, or like transfer functions, which just implement these two hooks. You subclass it, implement your transfer function logic, good to go. Here's sort of the class hierarchy of the upstream analyses and also wrappers. So we implement dense and sparse backwards and sparse forwards, and you kind of just subclass these and implement a few details, because the setting up the dependency graph, the logic for that is a lot of boilerplate, right? And so we have provided a set of like base classes that you can implement if you just want, I just want normal dense analysis. I just want classical sparse analysis. And then here we see there's dead cone analysis, constant propagation analysis, and also a recently added integer range analysis. So let's actually talk about those three. And we'll see what are actually the components of a dead code analysis. And these are subclasses of the things you mentioned above. We have 3 analysis states: constant value, which is the known compile time value of an SSA value, so like 4:I32. Executable, which is just, is it live or not? And this is attached to basic blocks and control flow graph edges. And predecessor states, which is attached to MLIR regions, because we do actually mix control flow graph control flow and region control flow in programs. The components of sparse forward analysis is the opposite. It's conditional by default, and so it takes into account the liveness of basic blocks and edges, and it produces like a state that's attached to each MLIR value. Now, important to note here is that if you don't have any analysis that actually provides a value for constant value, it actually takes a default. It takes the top state, which in this case is overdefined, which means if you run just dead code analysis and nothing else, it's just going to conclude that everything is live. No surprise there, that's the right default. And for sparse forward analysis, if you don't provide anything that provides a value for executable or predecessor state, it just assumes that the default values for these states is live, or not all predecessors are known, and therefore it's just going to run like non-conditional data flow analysis. So that's the right default. But if you combine these two analyses together, then you get something that's greater than the sum of the individual analyses. And that's really the power of the framework. We have SCCP is an optimistic, pessimist? It's a composition of 2 data flow analysis. And so we have data code analysis will determine which blocks are live, which then tells constant propagation which blocks to not have to worry about, and so you can get much more refined results of the analysis. There's also like a quick mention of interfaces. Interfaces are how you get like operation polymorphism in MLIR, and you can like, a typical pattern with some of these analyses is that you don't have to like implement a whole analysis, plug it into the framework, add a new transfer function. They just provide an interface. So instead of op folders, it's like give me your control flow successors, or maybe something else, like do integer range analysis on yourself. And so this is another mechanism that dialects can plug their operations into an existing analysis if that analysis provides an API that fits the use case. And so in dead code analysis, there's this like branch hop interface, which is a pretty common way to encode control flow in MLIR. And in constant propagation, we have, it's just the op folder, right? And you'll note here in this code that it does check if the operation is in a live block before actually doing the analysis on the operation. So another thing we can do is we can just plug in integer range analysis, right? Integer range analysis can do stuff that constant propagation can't. So you can take like, arith.min of a range from 0 to 10 compared to like 7. And say, don't really know the constant value of the result, but if it was 20, the integer range analysis can conclude that the constant value of the result of this operation is going to be true. Wait, did I say min or less than? Oh, never mind, less than. So if like compare less than the range of 0 to 10 to 20, the result is false. And you can actually use this in dead code analysis. And so what it does is you just add in more analyses and they compose together and augment the overall result of the analysis. So that's pretty cool. Here's an example, a concrete example of a select operation and a max. Constant propagation gives up on the select because it doesn't actually know what the condition is. But integer range analysis will conclude, actually, this %0 is between 0 and 3 inclusive. And so it can conclude that the results of the max is going to be 7 for sure, because 7 is greater than any number on the range 0 to 3. And so range analysis will conclude that the constant value of %1 is 7, and so %1 ever gets used somewhere in like a conditional branch, then dead code analysis knows how to prune that. And so they just kind of work together and sing in harmony. There's some known issues with the framework. Number one is directly subclassing the data flow analysis class is not super trivial because the dependency graph can be tricky to set up in a manner that is efficient. It's also hard to control the iteration order and convergence speed of the solver. Most data flow analyses are quadratic runtime in the worst case, and you can get them to linear time if you manage to run them in the right order. You can do this within one analysis, but getting all the analyses together when you don't even know what they're doing, and that's kind of the point of the framework, is you don't have to know what they're doing, is a little bit tricky. But it can be done. It's just there really isn't a nice API for it. And part of this is also just the cost of abstraction, right? The cost of abstraction is not having to care what's going on in someone else's world, and so you can't really optimize that. That's it. So I'll pass it back to Tom, who will talk about Flang and how they're using it.
Thanks, Jeff. So Flang is Fortran front-end, part of upstream LLVM. Don't mix LLVM Flang up with classic Flang. Classic Flang is a completely different compiler that also lowers to LLVM IR, but the code bases are not related. LLVM Flang is quite new. It's not yet ready for production use, but it's definitely ready to try. The expectation is that valid Fortran programs will run and produce correct results, although there's a few known issues if you look at the GitHub issues. If you'd like to try it, you'll need this undocumented Flang experimental exec when you're linking in order to produce an executable. That's just to discourage people from using it in production yet. So Flang uses a normal compilation flow. We starts with parsing and semantic analysis, as you'd expect. Then we lower to MLIR dialect for Flang, which is FIR, the Fortran intermediate representation. And then there's a lot of passes that run on FIR. Some of them are upstream MLIR passes. Some of them are specific to Flang. And then eventually we end up with LLVM IR. So this is an example of what FIR looks like. So the Fortran program is on the right. When we call bar, the brackets around x means call bar on a copy of x. Otherwise, Fortran is normally passed by reference. So the details of what exactly is going on in the FIR don't matter. It does what you'd expect. It prepares the arguments. We allocate an array to copy into. We copy into the array, and then we call bar on the temporary array, and then we return. What I want to highlight here is that you can see the composability of MLIR, where we're using lots of different dialects. So the function is a part of the function dialect. We've got lots of things in the arithmetic dialect from the FIR dialect, etc. So I'm going to talk today about the pass I added to Flang using the MLIR Dataflow analysis framework. So I was adding OFAST to Flang a few months ago. One of the things that came up in review is that other Fortran compilers have a feature at OFAST called stack arrays, where temporary arrays are allocated on the stack instead of on the heap. And it's just sort of assumed that a 64-bit machine is going to have a big enough stack to stick arrays onto. Flang already allocates real variables on the stack, and then you can configure a particular pass to move them to the heap if arrays are too large. So all I was concerned with is temporaries that are created by the compiler, such as the one we saw previously. So the obvious way of implementing this would just be to have some sort of hook whenever the compiler is creating an array temporary to say, oh, should we create this on the heap or should we create this on the stack? But it turns out when compiling Fortran, there's a lot of places where you might create an array temporary. So in the end, the community felt that it would be better to have one pass that looks over the MLIR representation of the Fortran program and finds all the array temporary allocations and moves those to the stack later on. The problem with this approach is when you're looking at all these arbitrary heap allocations, not all heap allocations are safe to move to the stack. So we need to figure out when that's safe to do so. So if we imagine a subroutine that has a heap allocation, I'm going to be showing these examples in Fortran, but obviously the pass is actually operating on MLIR. This is just to make it easy to read. And actual Fortran code that says explicitly do a heap allocation here, Flang will still do a heap allocation because that's what the standard says. So in this example, we have a heap allocation, but that's obviously safe to move to the stack because the allocation is freed, deallocated, within the same stack frame as the allocation. So there's no chance of the pointer lifetime outliving this stack frame. So we need to be able to analyze code to figure out, well, is the pointer lifetime appropriate? So the first case is that there's some code using the pointer after it's deallocated. Obviously, this is undefined behavior, so we don't really care too much about this case. The more difficult case is if there's some code using the pointer while it's safe to do so, so between the allocation and the deallocation. We have to think, well, is there anything that code could do here that would then make it impossible to safely move the allocation to the stack? Well, one of the more troublesome things that the code might do is store the pointer somewhere that persists longer than the stack frame. So, for example, it might allocate it to a global. But if you think about it, while it might be able to still access the pointer, as long as we know that the deallocation has happened before we leave the function, any access to that pointer after the deallocation is still undefined behavior. So what we really care about is the pointer deallocated by the end of this function? That's not always an easy question to answer. So if there's control flow involved at runtime, you need some sort of data flow analysis to figure out if we definitely hit the deallocate operation or not. So I used Jeff's framework to use dense data flow analysis to figure out are all the allocations deallocated by the end of the stack frame. So in dense data flow analysis in MLIR, the program point that Jeff mentioned is any MLIR operation or the start of each block. So there's in data flow analysis, there's what we call a lattice, which is the sort of the collection of all the state that the analysis generates. A particular point in the lattice is the state we have at a particular program point. So my point here is for my analysis at a particular point in the program, a MLIR operation, we're going to have a map of all the live MLIR SSA values, which represent heap allocations, to a particular state that we have determined about that allocation. That state could be one of four things. It could be we just don't know, the analysis hasn't visited this operation yet, so we have no idea what the state of that allocation is at this particular point. That would be a top value. We could have something that we definitely know that we don't know. So for example, if there are two different paths through the control flow graph and they both produce different results, then when joining those together, we don't know which is going to be taken at runtime, so we have to say that we really don't know. So that would be a bottom value. Or we can know that this pointer is definitely allocated at this point in the program, or we could know that this pointer has definitely been freed by this point in the program. So coming back to the example we saw before, I hope everyone can see that. The start of the function, there's no temporary allocation yet, so the lattice is empty. We don't store state about SSA values that aren't heap allocations of arrays. And then we have a third LLVM operation, which allocates an array on the heap. After that, all the lattice points will say that SSA value 2 has been allocated. Then we proceed through here. There is some control flow here, but because the result of the analysis inside the control flow and after the control flow match, then we can carry on with the same value. And I'll show more examples of that in a minute. And then after the pointer has been freed, we then know for sure that it's definitely been freed. There's no ambiguity there because we always hit this line. So when we reach the function terminator, which in this case there's only one return statement, so there is one function terminator, we can read the state from that and go, aha, this pointer has been definitely freed by the end of the function, so it is a candidate to move to the stack. Here's a simpler example. If we, at the start of the function, we know nothing, so there's no state, there's no points in the lattice. Then, after the array has been allocated, we say %a is allocated, and then we have this if statement, and on one branch of the if statement, it's freed, but on the other branch of the if statement, we call some other subroutine. We don't know what that subroutine does, so we're going to just assume that the pointer stays at the previous value that it had. So when we get to after the if statement, we have to join the two branches of the control flow could have taken, and we see that in one case it's freed, in the other case it's allocated. So you have to assume that, well, we don't know what it is. So when we get to return, we can say, well, it might have been freed by the end of this function, but we don't know for sure. Of course, it's possible that do something did free the pointer, but because we're not doing interprocedural analysis here, we don't know that, so we're going to assume that the transformation wouldn't be safe in this case. If we then did free the pointer on the else branch as well, then the data for analysis would join two freed values together, and we go, aha, we know what this means. This means it's definitely freed. So then the analysis would indicate that it would be safe to move the allocation here. Now, you might wonder, like, can we really just ignore, like, what if do something does something else that could cause problems? Well, if it frees the pointer and then we free it again, that's already broken. So we don't have to worry about that case. And if it allocates again, it's an SSA value, so we can't overwrite it with a different value. So in the end, we can ignore the subroutine call. And finally here, I'm showing that not all control flow in MLIR is structured. You can have basic blocks and conditional branches the way you would in LLVM IR. This is how we lower, say, go-to statements or more complicated control flow in Flang. But this actually works the same way because blocks have predecessors and successors, and you just join so if you have two blocks that both jump to the same place, you would join those the same way you join two arms of the if statement. In this case, the control flow diverges, and it never actually converges again to a single exit point. There's one that terminates with a return and one that's a third unreachable, which is kind of like saying, right, we've crashed here, we can't go anywhere after that. So in this case, the analysis would join the two exit points of the function together and say, okay, well, on one exit point, it's freed, but on the other exit point, it's still allocated. So again, we don't know for sure that the allocation has been freed by the end of the stack frame, so the transformation would not be safe. But if we had freed on both branches, then, as before, it would then be safe, and the data for analysis would pick that up. So how would you write this using the framework? So there's the state I mentioned before. So the unknown version where we just haven't seen it yet is just represented as the MLIR value isn't in the map. So unknown here means that we've looked at it and there's no way of determining what the right answer is. And then we can say it's freed or allocated. And then we subclass abstract dense lattice, which is says that this is a program point for a dense analysis. So like I said, this is an operation or the start of a block. The lattice point has to know how to join with another lattice point. So this would be how you, when I say that you have different control flow branches and these need to come together, they would call, one of them would call join with the other one. Then there's the actual analysis, which is a subclass of dense data flow analysis, which is part of upstream MLIR. The dense data flow analysis sort of handles when to call each of these helpers. So you only have to implement a small amount of things. So visit operation means the analysis is proceeding through the program. We get to an operation, we look at it, we're given what the state was before, and we have to produce the state that's then there after. So in the analysis I've described, you look at the operation, is it an allocation? Yes, it's an allocation. Okay, we'll add that to the map. Or is it a deallocation? Okay, it's a deallocation. We'll make sure the map reflects that. And it's also set to entry state. So for my lattice value, that just creates an empty map. So that was what you do when the analysis starts, sets everything to a value that says, we really don't know, more analysis needed. And finally, as I mentioned, in my particular analysis, it makes sense to ignore subroutine calls. In lots of other analysis, you wouldn't make that assumption. So the framework would behave differently than I've described for subroutine calls. If you want to change that, you'd override process operation. But for most of the time, you wouldn't need to do that. So if you want to run the analysis, my analysis builds on top of the SCCP analysis that Jeff was describing, so you need to load sparse constant propagation and dead code analysis, so that so the dense data flow analysis class uses the liveness computed by the dead code analysis to figure out if it's worth even considering a particular program point, and it just doesn't for dead code. So you need to have the dead code analysis running in order to for it to visit any of the operations. And then you just tell the solver, go, here's a function, or you could, I imagine you could probably do other operations, but mine's on a function. And then after the analysis is run, if it's succeeded, you can then look up particular states for a particular operation. You need to be careful because these might be null. So for example, if you look up the lattice point for a dead operation, then the analysis won't have even run on the dead code, so there won't be anything. You could also look up the state for other analyses, and that's used internally. So other things that the pass needs to make it work, it's not just, is the pass safe to do? When you're actually doing the pass, it's not always safe to put a stack allocation exactly where it is. So if you're inside a very long loop and you do a heap allocation that's then freed, it might be a bit slow with lots of allocation overheads, but at least the memory usage is going to be constant. But if you increment the stack pointer with every iteration of the loop, you're going to have a very, very big stack very quickly. So in this case, you'd want to make sure you put the stack allocation hoisted outside of the loop. But that's not always possible. So sometimes the stack allocation might be based on a value that's only available dynamically within the loop. So in this case, you might just say, right, we're not going to transform it. But in the end, we decided to save the stack pointer before the allocation and then restore it at the end of the loop body. So that then when we come around, it's like the first iteration again. So that's a lot more like the heap allocation. It's just slightly lower overhead. So like I said, you can't put, well, it's a very bad idea to put a stack allocation inside a loop. It's not always easy to spot loops in MLIR because it could be a loop in some sort of structured control flow like fear.do loop or some of the structured control flow while loops. But it could also be a loop in a control flow graph jumping between basic blocks as you'd have in LLVM IR. Flang can generate both kinds of loop depending on how people use gotos, so we have to support both. There's now an accessor in upstream MLIR that can spot loops of both kinds. As I mentioned, Also have to have the allocation after all the arguments are available. So if the arguments are only available inside the loop, you're stuck. And we need to be careful not to move allocations to a different OpenMP region. So doing all this isn't that helpful for spec benchmarks, but we found one Fortran program, Snap, which had a 23% improvement in runtime following this pass. So that's all from me. Does anyone have any questions?
Yeah, if you have any questions, there are 2 mics in the room, but I can also come to you.
Thanks for the talk. That was amazing. From the description of the sparse and dense data flow analysis, it did look like sparse analysis is the generalization of the dense analysis. And if this is the case, then why having the 2? And if this is not the case, what's the difference exactly?
So one is not a generalization of the other. You can write sparse analysis as a dense data flow analysis, but it's not efficient. And that's why they're separate, because if you want to have like efficient sparse analysis, you just use sparse data flow analysis. If you need something that isn't sparse, use the dense data flow analysis. And if you need anything else, well, you'll have to subclass the data flow analysis class.
So the short version I'd give for that would be that sparse is you'd have a lattice point per SSA value, but dense you'd have varying things as the program progresses.
Thanks for the talk. It was interesting. For the implementation of this data flow analysis on new dialects, should we follow the interfaces in the operations, or should we write a specialized class for doing the data flow analysis in our dialect?
If you can if your operations happen to fit in the interfaces that already exist, or if there's any opportunity for code reuse without like fitting a square peg in a circular hole, I would take it, right? And then any other case, right? Then that's what the purpose of the framework is: write your own analysis, plug it in, forget about it.
There was another question.
It was a great presentation. I was wondering if the framework is capable of interprocedural analysis or only intra-procedural analysis. Also, I was wondering if it is possible to discover infeasible states. So, like you have a condition and then a subsequent condition which are contradictory. Is it possible to discover that? So, do you use a set solver or an SMT solver or something like that?
So it can be interprocedural. I think by default, SCCP and dead code analysis are actually interprocedural if you have like private functions according to the MLIR symbol table visibility. And you can always implement interprocedural analysis using this, and then this can be done in various ways, like specialization, or you just like consider all call sites of a function. For the second question of, could you repeat it? I've already forgotten.
So, okay. So I have been working with the client static analyzer, and then we have seen that at some point we can reach up to infeasible states.
Right.
So that's a problem. We analyze infeasible states.
Yeah. So and the subclass of analysis state can implement a logic that would check that it is actually like non-contradictory. But beyond that, there's not really any facility to do so. But it can always be added. It's not super hard, given that the way the framework is set up.
Okay. And just getting back to the previous question. So the current state of the framework is still supporting the interprocedural analysis, or it is some future work?
So the interprocedurality is supported by the data flow analysis subclasses. So the current ones that exist, like dense, sparse, these actually will do interprocedural data flow analysis. But they do it in a particular way. There's other ways to do it, right? And you could always like forget about interprocedural analysis and not use it, but the capability is there. If you want it to be slightly different, like your call graph you want to treat the call graph differently, or if other semantics that you want to implement, then you can. Really, like, I'd say that the framework itself has no concept of something being interprocedural or not, right? That concept is implemented by one of the analyses that can like understands what does interprocedural mean. All it really means is that like call functions can go from one spot to another. And so it's not really like something that has to be encoded in the framework. It's something that could be implemented as a concept. And it is.
Just following up on the interprocedurality, that gets us into a question about context or path sensitivity, maybe. You said the framework is agnostic to that, but it likely doesn't provide facilities to build this right now. So have you thought about this aspect?
Personally, I think of like interprocedural analysis as just like, in the context of a framework, it's the same as control flow, right? But there's other semantics going on here like stack and exceptions, but you can conceptually conceive it as like a specialized kind of control flow. That may be a bit of a grand oversimplification. And yeah, there's questions about do you do path sensitive, do you not do path sensitive, and the version of interprocedural analysis implemented by the sparse and dense and dead code analysis are path insensitive, and so they don't like splat out the call graph as you traverse into function calls.
Okay, are there any other questions? Okay, thank you, Tom and Jeff. So we now